Hey everybody, Dr. Retzek here. This is our sixth and final video on section 6C and also our final video in chapter 6. What we've been doing so far is developing ideas of orthogonal complements and some sense of how to minimize the distance from a vector to a subspace. Today's discussion is all about seeing that in practice. So we have one example. Let's get started. So in this example, we have the good old XY plane, classic setting. So XY plane, like so. And we have 3 points of interest. We have the point 1 over 0 up. We have the point 2 over 0 up. And we have the point 0 over 6 up. So those are, once again, 1, 0, 2, 0, and 0, 6. Now, it's clear that those 3 points are not collinear. They don't all lie on a line. Yet, they look like they might be almost linear, or they might be data points in some relationship that we think is linear or nearly linear. And so our objective is to draw a best fitting straight line to those 3 dots. Now, with our eyeballs, maybe it would look something like this. Maybe like, I don't know, through here somewhere. Maybe like that. None of the dots is on that line, but somehow the total disparity between all 3 dots and the line looks to be minimized in some way. But apart from that, all of those statements are awfully vague. Linear algebra, the stuff we've been learning, actually gives us a route towards formalizing this idea. So we're going to find the best line, y equals mx plus b, to fit those 3 blue dots. Now, the reason no line actually goes through all 3 is that if you had a line passing through all 3, well, when you stick 1 in for x and 0 in for y, you would need m plus b equal to zero, and you would also need 2m plus b equal to 0. And you would also need 0m plus b to come out to 6. Now, you know with your eyes, there's no way that those 3 blue dots lie on a single line. But you can take a linear algebraic approach to this discussion and say the same thing by asserting that that system of equations has no solutions. M comma B. There's just no way to choose a slope and an intercept of the red line to make all 3 of those things come out true. Yet another way to say that is to think of this in a more operator theoretic way. If this were Math 206, you guys would express that system of equations and its lack of solutions as something like 1, 2, 0, 1, 1, 1 times vector m, b, coming out to answer 0, 0, 6 has no solutions. And if you were to investigate that question in a Math 206 way, you would find out it has no solutions. Put yet another way, thinking in a more 406 state of mind, I think we're saying this. This box, that's R2. T is going to be a linear map from R2 into R3. The way T works is T is going to work like this. T takes a vector x in R2 and does the matrix 1, 2, 0, 1, 1, 1 to that vector. That's how T works. So now what we're saying is no combination of these vectors here and here no linear combination of those two columns can come out to 0, 0, 6. In other words, the range of this linear map does not include the vector 0, 0, 6. Okay, fine. So there's no input that we could possibly plug in to land us at 0, 0, 6. There is no input m comma b that outputs 0, 0, 6. All right, fine. 0, 0, 6 isn't in the range. Well, if it's not in the range, is there something in the range closest to 0, 0, 6? We're looking for a vector in the range. Should we call it u? That is closest to 0, 0, 6. If we can find that vector u closest to 0, 0, 6, then we can backtrack and find the m comma b that produced it. After all, it's in the range. So some m comma b must have produced it. And that choice of m and b will be optimal in that sense for our original problem with the line. So our problem has become a linear algebra problem. We're trying to find the shortest distance from 0, 0, 6 to the range of that mapping. All right, and we know at this point that that shortest distance is some kind of projection. Okay, so here's what we got to do. Let u be the range of t. So that red blob, that's u. Now we already know u equals the span of, well, it's the span of the two columns of the matrix. So it's everything you can build out of 1, 2, 0 and 1, 1, 1. That's the very definition of the range of that matrix multiplication mapping. In fact, you guys might have called it column space back in the day. Whatever you called it, u is equal to the span of those two vectors. For the purposes of projecting into the subspace U, however, it's much nicer to have an orthonormal basis for the red blob. So even though 1, 2, 0 and 1, 1, 1 are a basis for the red blob, we'd much rather have an orthonormal basis for figuring out what is that closest vector u to 0, 0, 6. All right, well, you know what to do. You have a basis in your hands and you wish it was orthonormal. You let Graham-Schmidt go to work. Let GS go to work on these. Okay, now I'm going to tell you what I got. I actually did this by hand. It's not that bad because there's only two. Here's what I got for the new and improved orthonormal basis. I got E1 is equal to the vector 1 over root 5, 2 over root 5, comma 0. That's easy. You just take V1 and divide by its length. And then E2 took a little work, but not bad. And E2 turned out to be 2 over root 30, comma, negative 1 over root 30, comma, 5 over root 30. Now you can check that E1 and E2 are both unit vectors. They are orthogonal to one another. And the bonus feature of Graham-Schmidt is the span didn't change. So U is also equal to the span of E1 and E2. Now, once you have an orthonormal basis for the subspace you're trying to project into, then you know for sure if you call this vector V, so let V be 0, 0, 6, then the projection into the subspace U of that vector V, you know it. This is what it is every time. This is from the proof of theorem 6.47, I think. You just do V inner product E1 times E1 plus V inner product E2 times E2. Now, V, E1, and E2 are known. Here's V. Here's E1. Here's E2. When the dust settles, I'm going to tell you what I got. I just did this by hand. I just multiplied all this out, and I got this. I got the vector 2, negative 1, 5. That's friendly. Okay, so let's see where everything stands right now. 0, 0, 6 is not in the range of this mapping. 2, negative 1, 5 is in the range of this mapping. In fact, it sits right here. Let's say this vector here is 2, negative 1, 5. And we can say what input vector back here produced it. You guys can check that the vector negative 3, comma 5 is the one that gets sent to that vector U. And that vector u is the closest thing in the range to 0, 0, 6. In other words, though 0, 0, 6 is not in the range, there is something closest to 0, 0, 6 that is in the range. And if we use the line, the choice of m and b that makes that object 2, negative 1, 5, well, we'll have a line that, in the sense of our drawings, is, quote, close to the 3 dots. In summary, the choice m equals negative 3 and b equals 5 makes a line that is, quote, closest to the 3 dots. In the sense that the distance from 1 to 0 m plus 111b take away 0, 0, 6 is smallest when m is negative 3 and b is equal to 5. And if you actually write that down, come back to our original drawing, all the way up here. We just figured out that the best line is y equals negative 3x plus 5. So first, look at that with your eyes. That's pretty solid. That looks pretty decent right there. That red line we drew with our eyes, I think, is pretty close to y equals negative 3x plus 5. And not only that, the sense in which it's the best line is that these 3 errors, error 1, error 2, and error 3, they are minimal in that e1 squared plus e2 squared plus e3 squared has been minimized. Because that is this norm. This right here, this equals square root of e1 squared plus e2 squared plus e3 squared. And this actually has a name. This is called the least squares approximation, and it fits a line, 2 data points. We used 3 data points in our example, but if you just had a giant scatter plot of a bunch of data points, this method would produce the best fitting line, where best fitting means e1 squared plus e2 squared plus e3 squared is minimized. Now, if you don't like that definition of best fitting, that's fine, and there's all sorts of other definitions of best fitting, but this is certainly one of them, and it's the one from stats class. And seemingly out of nowhere, vector projections is what proved it for us. So that's a nice example of using this idea of minimal distance to a subspace. The book also does a nice example in a totally different setting where we're talking about subspaces of vector space of continuous functions, and the subspace consists of certain polynomials. You have a homework problem this week, same idea. But zooming out from all of those, the crux of the matter is this. If you are trying to approximate something that doesn't belong to a subspace, use the thing in the subspace closest to it as your approximation. All right, that's it for chapter 6. We know all about inner product spaces now. Let's shift our focus and get dialed in so that we're prepped for the exam on Saturday, and then we'll make the transition to chapter 7. All right, see you next time.